Hey people, so with the pandemic, a lot more of us have been trying out things like virtual races. And now some of those have even pushed it so that you're actually competing for real, not just going out and covering a distance in order to get a medal for yourself, but going up against other runners around the UK on time-based kind of challenges, such as the England Athletics 5K Championships. Now, one of the things that we wanted to check out here on the Run Test, is we're always testing watches and we're looking at GPS in great detail, was actually how much are we able to rely on those GPS reads if we're doing something that's a time-based race? Are they reliable? Is it a level playing field? Is everybody actually running the same distance? So on our travels as we test things, we came across a company called FocalPoint. Now FocalPoint have been working with a solution that they claim is a lot more accurate than the GPS that we find in our phones and watches and all those things that power your apps and your regular day-to-day kind of wearable trackers. They say that they can actually not only mark our course better, but they can also get our distance down to far more pinpoint accuracy, even down to centimetre level. So they can put you in a space on the planet within centimetres and not within metres. So what we wanted to do here was actually take a look at how that technology works. And also I'm just about to go out and do a big long run wearing several devices. I've got 5 or 6 watches on me, including the sort of top brands, some of the top watches, a couple of pods and some other bits and pieces to see how FocalPoint, which is in this app on this phone, will measure up against those other devices. And also then hopefully we'll talk to FocalPoint about why that might be, why you might be getting different reads even though you run the same route over and over again, or in fact you run with a watch and a phone and you're coming up with different stats on your app and on your watch. This video will show you why that might be happening. So that's the 5K done, still a bit sweaty, it's a little bit rainy too, but I'll run you through the numbers. So let's take a look at how those devices fared. Well, the raw GNSS from the phone clocked 5.11 kilometres. FocalPoint came in at 5.08. The Chorus Apex Pro came in at 5.02, with the Stride just behind it at 5 kilometres dead. The Garmin Fenix Pro clocked just under at 4.95, and the Polar Unite, which is actually a phone tethered connected GPS read, was using our phone, came in at 4.94, so that's interesting, and the Polar Ignite came in at 4.90. So what you've got actually here is around a 200 metre variation across all of our devices that we used, and actually over a 5K distance where you might be racing for time, that could be quite significant. So that's how the numbers stacked up in our test, and to find out exactly what's going on when we're tracking with GPS in various different devices, I caught up with Dr Ramsey Faragher. He's the CEO of FocalPoint. He's also one of the world's leading experts when it comes to GPS and satellite tracking, and I caught up with him on a Zoom call to find out what's been going on with our GPSs and also to get some insights into the kind of things that you can do to make sure that you're getting the best fix and the best trace when you go out and run. Now, as a runner, when I step out at first and I hit start on my watch, what's happening there that could be influencing my overall accuracy of the results when I get to the end of my run?
Yeah, the very first fix is really important, and the very first few seconds that your device is seeing the sky and picking up data from the satellites is really important. And there's a number of reasons for that. So the first one is that the device actually downloads some data from the satellites. This is a big difference between using your smartphone to run and using a watch or another dedicated platform to run. So with smartphones, the technology has been built into the chips in them for a long time, such that all the data they need about the satellites gets sent over the mobile phone link. And so you can fire up a GPS on your phone, and within a few seconds, it can be working very well. But with standalone devices, it takes between, say, 20 and 30 seconds typically to actually download the data from the satellite. So depending on exactly what sort of platform people are using, what they're running with, it might be the case that if they've got Strava running on a phone app, they can kind of go out straight away and they'll have a much better early kind of 30 seconds, minute to the run than if they tried to just go out with a standalone watch or another standalone device that actually has to download the data. And that's why you'll get instructions to kind of wait for your device to have had a minute to lock and all this kind of stuff. But the other thing that's important is that the GPS receiver tries to smooth together and fuse together data over a number of seconds. And once you're out and moving and you've had a good few minutes of GPS fixes, it sort of uses the data it's already got to decide if it thinks the next piece of data is wrong or not. And so it has some way of trying to throw away a bad measurement. And it does that basically by saying, do I believe that I've now leapt 100 meters? Maybe not. So I'll assume the new measurement's wrong. But the very, very first fix you ever get, there isn't anything for it to compare against to decide. So it just trusts that one. And so if your very first fix is like 150 meters wrong, then it will take you probably 100 meters of movement and half a minute of running for the system to kind of get rid of all of that error and dial itself in and drag itself to the true location. And so it's not a good idea to just sort of run out your front door if you're wanting that particular run to be a good one that's well metricated. You really want to let your GPS receiver get a good view of the sky. And that might be that you go to the top of your house and actually the signals will come through your roof much better than they would if you're standing downstairs by your front door. So if you want to have your GPS lock inside, then do it at the top of your house, not at the bottom of your house.
That's a good tip. So even though you're indoors, that's still potentially better than stepping out and standing right by your front door.
Yeah, so if you're at the top of your house with just your roof tiles and your loft insulation in the way, your device will probably still have a good chance of downloading all the data from the whole sky. But if you're stood just inside or just outside your front door, it's got to go through all of the brick of your walls and your roof as well. And it will probably only download half the sky that stood at your front door, whereas inside your house with just the roof in the way at the top, it might be able to see all the sats.
If the first fix is wrong, eventually will it catch up? Or is it possible then that as I move through my run, the subsequent fixes can all be wrong?
Yeah, so you can get into this horrible situation of lots of things compounding, and it's certainly possible to get horrendous positioning all the way through a run. So the first thing is that for the devices that need to download the data themselves from the satellites, that's 30 seconds, let's say, to download the data. Unfortunately, the GPS signal is not very clever, and neither are the receivers, and they need to see an uninterrupted 30 seconds. And if it gets interrupted, they have to wait for that message to start again and then read the whole 30 seconds again. So for satellites that are quite low down in the sky, if you go for a run and it's just periodically flicking between trees, buildings, and clear sky, if there's never a 30-second clear view of that satellite on your entire half an hour run, you'll never download the data from it. So you can have that kind of problem. And there's the fact that when the constellation changes, in other words, if you do run close to some buildings, so you've lost half the sky, and then you run out into the open and you can see the whole sky suddenly, that will give you this shift in position. There'll be a new best estimate as to where you are when you can see more satellites. And so that inevitably causes the positions to hop around as well. And so the sort of ideal scenario is that you're only ever seeing the same good set of satellites all the time, and you're not actually constantly flicking between half the sky because there's buildings here, and then suddenly a different half of the sky because now there's buildings here, and so on. So it's a problem of GPS-only devices, or should I say satellite-only devices, that simply buildings around you cause a lot of problems. And the only way to get around that is to get rid of the buildings or add more sensors into the platform instead.
And is that why when people look at maps after their run and they see that they've maybe run through buildings and whatnot, is that related to that fact? That's why you're getting data that isn't quite accurate?
Yeah, so if you run tight up against a row of houses, for example, and you only see one half of the sky, it's what we call a bad signal geometry. And it's literally the point is that you want the signals to be coming at you from all directions. And that kind of gives you there'll still be some error, but you're centered on the right place. If all of the signals are coming from one direction, it inevitably actually pushes you away from that set of satellites. And that's why you can get these instances where it looks like you're charging straight through buildings. It's because you're seeing a poor signal geometry and you're being projected into those buildings away from the only satellites you can see.
When it comes to like a running watch versus a phone, what are the key, I guess, bits of hardware difference that make the biggest difference?
Definitely that point I said earlier about the difference between a phone and its access to the mobile phone network or your Wi-Fi in order to what's called hot start the GPS chip and just force feed the GPS chip with all the relevant data for right now about the satellites. That's a really big difference. And so a smartwatch that can talk to your phone or can go on the Wi-Fi and get that data is going to perform much better than one that can't talk to the internet. Then you've got where the antenna is in the device is going to be really important as well. So the antennas inside both the smartwatches and the smartphones are really tiny. So ideally, you'd have a GPS antenna that's comparable to the wavelength of the signal, and that's 20 centimeters, right? So no one's going to have a 20 centimeter dish on their head, but that's what the really expensive survey grade GPS antennas are. If you ever see them on tractors or on autonomous vehicles or people with them on survey poles on building sites, they're this big. But that's because if you've got something that big, you're going to get the best possible reception of the signals. Instead, the little bit of wire that is inside your phone or your watch is probably about the length of one of your fingernail clippings, if you're lucky, typically smaller than that. And where exactly they're shoved in the watch or the phone will make a big difference. So on the phones, they try to run them around the edges, and therefore it's kind of, if it's mounted to your arm or something, then hopefully the antenna's on that top edge and it gets a good view of the sky. You might find that putting exactly the same phone the other way up and down in your pocket, you might get really bad performance because the antenna is now pointing at the ground and got your body on top of it. And similarly for watches, it will really depend on where the watch manufacturer has packaged that antenna. And if they've kind of squeezed it in there because they think they should chuck a GPS chip in there, or if it's designed for purpose, this is a running watch and we've decided that most people are going to wear it on this wrist and we should put the antenna there and so on. So the antenna placement's a really big factor. And then the last bit's the extra sensors they can put in the device. So having accelerometers, gyroscope, barometer, and a compass helps greatly, because when the GPS signal is not available, you can use those to propagate your estimate of position instead.
Some people will go out and they'll wear their watch and they'll track with their phone and they'll get the same read, or they'll get a completely different read, or they'll run a known distance that they do all the time and use their watch one day on a Monday, and then on a Tuesday they'll get a totally different read. What's happening with those two examples?
Going out and doing exactly the same run with exactly the same gear at exactly the same time, you don't have exactly the same pattern of satellites. And that's one of the factors, an important one. So there are 4 constellations: the American GPS, the European Galileo, the Russian GLONASS, and the Chinese one called Beidou, or Compass. And they've all independently designed those systems. The time it takes for the satellites to orbit is slightly different for all of them. So for GPS, if you want exactly the same pattern of satellites above you tomorrow, you actually go out 4 minutes earlier tomorrow. So the constellation repeats actually every 12 hours and 2 minutes earlier every 12 hours. So 4 minutes earlier the next day. But for the other constellations, that's not 4 minutes. It's a different number. Still on the same order, but a different number of minutes. And so to get exactly the same sky again across all the constellations, that only happens a handful of times in the entire year. And so if you go out at lunchtime every day, then what will happen is one day you'll go for your run and there'll be the nasty bit with the worst bit with buildings either side of you. And on one day at exactly 12:04, you can still see 8 satellites and you're getting an okay fix. The very next day at 12:04, you go down exactly the same place, different pattern of satellites, you've only got 6 this time, and the positioning will be worse. So that's one key factor there. The aspect of things like I've got a watch on this wrist and a phone on that arm. Well, there's lots of things there. Only only a few centimeters difference in position of two devices can actually give totally different position fixes. So you could put on the same arm, you could put two identical watches that have got exactly the same data from the satellites. They're locked onto the same satellites, but you could run down an urban canyon with tall buildings either side of you, and these two watches, 5 centimeters apart, could give you 100-meter position differences. And this is caused by one of the nastiest things that we have to fight as GPS experts, which is called multipath interference. And what this means is it's the pattern of reflections from the buildings mixing with the true signal you want. So the buildings cause reflected signals. You've got the line of sight. This watch has a particular collection of the line of sight and the reflections from two of the buildings. This one that's 5 centimeters different on your arm, those reflected signals are only a few centimeters difference in their path length, but the way they interfere with and corrupt the line of sight signal you want is different, and it's different enough to corrupt the overall signal estimate by up to 100 meters.
But it's fascinating, isn't it? Because actually, I think we're so programmed to think that this tech is almost infallible. We expect to go out and for it to perform the same day in, day out at the same time. And there's so much going on here. I wanted to get your thoughts on what this really might mean for competitive racing that's tracked using GPS and devices.
But right now, this era we're in right now, the devices are simply not good enough to use to decide who's won a race. It's the equivalent of, instead of timing with a nice accurate watch that can time to 1,000th of a second and using that to decide who won the race, it'd be like putting a pendulum clock on the deck of a ship in a storm and using that to time who won the race. You're just using the wrong caliber and quality of the technology at the moment to do something like decide who won the race. But hopefully we'll get there in a few years' time.
Yeah, I mean, I guess some of these guys, they're doing it, it's almost out of the necessity of the current situation and they're trying to do the best thing, but I think it's really useful for people to understand what the current limitations are. And that leads me on to what's FocalPoint's vision for fixing this? What are you bringing to the table that's going to help us with this problem? I mean, not just for fixing kind of competitive racing, but actually just more for everybody in the street to help us get better, more accurate, more reliable information about our runs.
Yeah, so we are positioning experts who are concentrating entirely on trying to make the positioning technologies on consumer devices much, much better. So we used to do things like build Martian rovers and the navigation engines of nuclear submarines and stuff like that. And now we're having great fun revolutionizing the low cost, low power stuff in consumer devices. And there's two main impacts we're having. So the first one is that we've redesigned how the GPS receiver calculates its measurements internally. So it's this new award-winning technology that we've invented, which completely changes how that electromagnetic radiation from the sky is turned into measurements of distance to the satellite. And fortunately, we can just change software inside the chip to make this change. People don't have to actually design and build a new chip, which is great, but it's still taking time for the GPS chipset companies to integrate our changes. So that's still a few years away. But one of the most important things about these new types of GPS chip is that our technology is the only one that can tell the difference between the true signal that's coming from the satellite and a reflected one that you don't want. And so we actually remove that multipath interference I described. So two watches on your wrist, 5 centimeters apart, with our new receiver design would record accurate positions, both of them. They wouldn't have this multipath error I described earlier. The other thing that we're doing is we've developed a very complicated and very advanced human motion modeling system. So this uses the accelerometers, gyroscope, barometer, and compass inside a smartwatch or a smartphone, and it gathers data from them and can reconstruct how you're moving through space. And so you combine that with a GPS receiver, and it means that we can provide a centimeter level understanding as to how you're moving. And so the human motion modeling system actually provides 200 measurements per second as to how the devices move through space. whereas a GPS receiver gives you 1 measurement per second. So it's giving a much higher resolution understanding of what you're doing.
And that can literally put you, if you've got a one path that's on a certain level and another path that's slightly higher, but they're running parallel, it can figure out where you are, whether you're on the upper level or the lower level, right?
Yeah, you can do stuff like come into your house and run up the stairs and go back into the data, and you can count how many stairs there were. So, we've got that level of resolution as to what's going on when you move.
And interestingly, actually, that's the other point, that it works indoors.
Because it's just based on modeling human motion. So if there is no GPS fix at all, then what the human motion modeling system does is it returns how far you've gone, and it can return a trace that reconstructs the actual path you took, but it doesn't know where on the planet that was or which way around it was oriented. And so it still needs GPS information to actually do that bit and shove it in the right place on a map. But yeah, it works indoors.
And as a runner, when am I going to see this coming? How will I engage with it? What is it? An app? Is it a piece of hardware? How will it appear for me?
Yeah. So the really great thing about the human motion modeling system is it doesn't need any changes inside the GPS chip. So we're rolling that one out much more quickly, and it will come as an app to some testers like yourself. But we aim to have it deployed inside the devices. So we're hoping to have an announcement at the end of this year. There's a company that I can't say who they are right now because they're still integrating our technology. So if anyone used them right now today, I don't want them confused that the line they're seeing is ours, because it's not. So when they finish our integration, when we announce that we're in their platform, that's the first sports fitness device that's going to contain our tech, and that should be an over-the-air update for all their customers in about September time. And we're discussing with a bunch of watch manufacturers as well right now, integrating with them. So we would like the watch manufacturers and the smartphone manufacturers to integrate our software themselves in the operating system, and then whatever preferred app or technique all you runners like to use, you can just use that. You won't have to just use the FocalPoint app, because that's what we want. We want you to use whatever you want, and we'll just provide brilliant latitude and longitude to you, and that's all we'll do.
And then the benefits of that on a runner's level, the benefits we're looking at are things like more accurate real-time pacing, or no more thinking that you've run too far in a marathon. You'll know exactly the distance that you've run, and all those kind of benefits are going to come for runners.
Yeah, we typically get about 1% error on distance traveled. So still a little bit of improvement to come over the years as we add more cleverness into it. But from a lot of trialing that we've done and things that we've seen other people do, we're competing at the moment with things that are more like 10% error. So we're going to be able to provide a significant help, especially to the aspects of, as you say, things like live pace. A lot of the live pacing technology at the moment is based on the GPS information, and you can have these sporadic large errors, which the human motion modeling system is just not subject to. So much better live pace and live distance travel estimates for sure.
So there you have it. That's pretty much everything you're ever going to need to know about satellite tracking and how it affects the accuracy of our run data. Perhaps it'll stop you doing zigzags up and down outside your house when you finish a run to try and clock over that final kilometre or mile. And maybe it'll even stop us all asking that question about whether or not the marathon courses were too long or too short in the future when FocalPoint's tech comes baked into our watches. Don't forget to like and subscribe if you enjoyed this video. It was a bit of a long one and a deep one, and we'll be doing some more of those in-depth looks into the technology that we all use in future. So if you want to hear about more of those, hit like, subscribe, notifications bell, all of that stuff, and we will alert you when we've got more videos. But thanks for listening. If you made it this far, well done, and we hope to see you again on the Run Testers. Thanks a lot.